All right, welcome to Chapter 2, Part 1 video. I'll be skipping through the slides that we went over in class. So the first 4 slides on your notes packet from the topics page are those 4 slides that we did together in class. What we'll learn about in this video: polynomial functions, which we reviewed today or last class, average rate of change, association, correlation, and linear modeling. This has to do with regressions that we looked at a while ago. Characterizing linear functions, so what is it that makes a function linear? Quadratic functions and their graphs, characterizing quadratic functions, and applications of quadratic functions. So some of this should be review. A lot of the transformations and function properties and things should be review, but then applying those to the characterizations, that's our next step forward, our digging deeper into this topic. So why do we care so much about this topic? Many businesses and economic problems are modeled by linear functions. Models based on quadratics and higher degree polynomial functions are used in science and manufacturing applications. We'll be seeing specifically how it's used in free fall, such as skydiving or dropping an object for quadratic functions, and then as well some financial applications in the homework, in the practice next class. So let's start by reviewing how to find the equation of a line. This was some feedback that I got from the project, is that we don't remember very clearly how to find the equation of a line. Hopefully you've already had the chance to review that through the project. So we'll just go through this pretty quickly. In this notation, we have a linear function f such that f of -1 equals 2 and f of 2 equals -3. So we know that gives us 2 ordered pairs. Our x value here is -1 with a y value of 2. And then our second ordered pair has an x value of 2 and a y value of 3. Right? Remember that f of x is just another name for y. So when we're finding f of a value, that function value is a y value. So that means 3 is a y value and 2 is a y value. And the x value is the one that substitutes in. So our x values here are the ones that are substituted in, -1 and 2. Okay, so how do we find the line from here? Well, we actually have a couple of options, but no matter what, we are going to need to find the slope. So let's find our slope, which we can think of as rise over run, or change in y divided by change in x. If you're not familiar with this notation, that little triangle is delta. It's a Greek letter. And it means change. So we're just looking at the difference in y values, y2 minus y1, and then our change in x, x2 minus x1. So if I call this point 1, this would be x1 and y1. If I call this point 2, that would be x2 and y2. Be careful. What I often see is trying to call this x1 and x2, and calling this y1 and y2, but this is not a y value and this is not an x value. So be careful of that. That's one of the most common mistakes that I see for this type of question. So here we're gonna find our change in y. So y2 minus y1, that's 3 minus 2, divided by change in x, that's x2 minus x1. 2 minus a -1 turns into a plus. 3 minus 2 is 1. 2 plus 1 is 3. So there's our slope. And then we also have to find our y-intercept. So how we can do that is we can start substituting this into one of our formulas. We actually have 2 formulas we can use. We can use the slope-intercept formula. And this is the one that I find most students prefer. Y equals mx plus b. But technically, we should use the point slope formula. Now, both will give you the correct answer. One is just a little bit more like a hack, and one is really a formula. So we'll start with the point slope formula. It's y minus y1 equals m times x minus x1. Now keep in mind, both of these should give us the same answer. So if you have a preference for one over the other, you can use that one, but technically the correct way to do this is the point slope formula. But if you prefer slope-intercept again, you can still use that. So what do I mean by y minus y1? Well, y is going to be my variable that will stay in my equation. So I should end up with that y in my final equation. y1 is a value I'm going to substitute in. It's my first y value. So that was 2. Y minus 2 equals m we found is 1/3. Just like the y's, the x without a subscript stays in my equation. The x with a subscript is the one I'm substituting in for. So minus a -1 again turns into a plus. From here, we're solving. So I'm going to distribute that 1/3. Y minus 2 equals 1/3 x plus 1/3. Add 2 to both sides. In order to add 2 to the 1/3, I need a common denominator. Our LCD here is 3. So we have y equals 1/3 x plus 1/3 plus 6/3. So our final answer, y equals 1/3 x plus 7/3. Now let's see if we can get the same answer with the slope-intercept form. Again, I have the slope, I'm going to substitute that in, but I'm also going to pick an x and y to substitute in because I don't have b. So I need to find b, and that's what makes this a little bit of a hack, because I'm not going to substitute this in and get an equation like we did in point slope form. I'm going to substitute, get my value of b, and then substitute again. So let's use that same point. We'll use -1, 2. So my y value is 2 equals 1/3 times x is -1 plus b. Now we substituted for the y and x because I don't have a b. So I can't continue forward with this equation unless I find that value of b. So I substituted everything I could in order to find b. So we have 2 equals -1/3 plus b plus 1/3 plus 1/3. Notice that's exactly what we had on our right side here, 2 plus 1/3. And so we already know that what we should get is 7/3 equal to b. Okay, so now that we have b, we have to substitute that back in to y equals mx plus b. And this time leave our y and x. So y equals 1/3 x plus 7/3. So we get the same answer, okay? And you can use either method, but if you look at a textbook or if you look online, almost always they're going to say to use point slope because that's the formula for finding this line. Okay, let's take a look at our next page. Here we're looking at polynomials. So we defined polynomials in class, and we talked about their degree and their leading coefficient. And now we're using another kind of format for defining polynomials. Now it means exactly the same thing, but instead of calling all of our coefficients a values and then numbering them from 0 to n, we're just going to give them different coefficients in this table. So this is another way that we can list our polynomial functions. Starting with our 0 function. Now 0 is special because if I have f of x equals 0, this is actually the y-axis. Sorry, the x-axis. If y is 0, that gives us the x-axis. And if we're on the x-axis, right, that means that I have all of my points are on the x-axis, which is what we called our zeros. Our zeros are the points that cross the x-axis. So the special property of our 0 function is that we say it has an undefined degree. Okay, even though 0 is a number, it's kind of a special number. So we say its degree is undefined because it is infinitely many zeros. It has infinitely many points on the x-axis. So the 0 function is special. We treat it special. Other constant functions, any other number, if it's 1/3, 1/2, -8, -2/5, any number other than 0 is considered a constant function. And that will have a degree of 0, right? Our slope is not changing. And so if I have a degree of 0, that means I am a constant function that's just a horizontal line. And that means I will have no x-intercepts. If I have a horizontal line, it will never cross the x-axis. So it has 0 zeros. No solutions, no x-intercepts. Our next degree, notice now we have ax plus b. So we have now for the first time x in our function. And that is what's going to give this a degree of variability. It's going to have a function that changes. It's not constant anymore. And we know our linear functions can have a positive slope or a negative slope. They have a degree of 1 because the slope is the same for the entire function. So our degree is 1. Notice the exponent of x, also 1. And that will have 1, 0. No matter if it's a positive slope or negative slope, it will always cross that x-axis 1 time. Our next type of polynomial is our quadratic function, quadratic meaning x squared. And so our degree is 2. It can cross the x-axis 2 times, up to 2 times. So the number of zeros, it can be 0, 1, or 2. Our next function is the cubic function. Again, we have a degree of 3. And that means that our function can have up to 3 zeros. Up to 3 zeros. It can cross the x-axis 1 time, 2 times, or 3 times. This time, it cannot cross the x-axis 0 times. I'd like you to think about that, and we'll discuss it next class. Why can't the cubic function cross the x-axis 0 times? And then we have our next degree, which is the quartic function. You can also call it the 4th degree function. Our highest exponent on a variable is 4. The degree, therefore, is 4. And it can cross up to 4 times. This time, 0 is included. Okay, so why can 0 not be included in a cubic function, but it can be included in a quartic function? We'll discuss it next class. Okay, so let's look at how we can use our knowledge of polynomials to define a new term, and that is average rate of change. The average rate of change of a function is when y is our f of x, so y is our height, for any two x values, a and b. So what that looks like, if I'm looking at a graph, I can pick a and b, and whatever my function is doing, I'm going to take the height of the function at those 2 points, a and b. And then what we're doing, this height, f of a and f of b, we're essentially finding the change in y values, right? Here's f of b, here's f of a. We're finding the change in y values divided by, and then our difference of b and a. That's our change in x values. That should look familiar, right? We found the change in y divided by the change in x. And that's our average rate of change. If you think about it, how much is it changing over that period? Well, it changes, and the rate of change changes, the slope, the steepness of the graph changes, but the average is what if it changed the same the whole time, right? The average is kind of evening it out. And so our average rate of change looks like that red line. It's calculating the slope of the line between those 2 points. And that's why this should look familiar. This is the same as calculating slope, the same formula. Okay, so how is average rate of change different than slope? Why don't we just call it slope? Well, for a nonlinear polynomial function, and really for even non-polynomial functions, for a nonlinear function, if the average rate of change is between 2 points that are not connected by a line, right? If it's nonlinear, then the rate of change can change between those 2 points. The steepness of the curve changes between those 2 points. So the curve doesn't create a straight line between those points. The slope is a constant rate of change. Only lines have slope. Only straight lines have slope. So that's linear functions, okay? When I have a higher degree polynomial, think about the blue curve that I drew, okay? That does not have a straight line between those 2 points. So my average rate of change doesn't tell me anything about the rate of change at any point on that function. It only tells me the average between those 2 points. So an example, if I'm driving from my house to school, maybe I drive 25 in my neighborhood, and then I get to a main street that I can drive 35, and then I get to the freeway where I can speed up to 65. And then I exit the freeway and I drive 25 through the neighborhood all the way to school. Okay, I probably slow down closer to 10, really close to campus, because there's a lot of unknowns there. There's cars that could be pulling out, or children can be crossing the street, families can be getting into their cars or walking their dogs, right? So the whole time that I drove there, my speeds were 25, 35, 65, 25, 10, let's say. Well, my average speed might have been 40 miles an hour if I average all of my speeds over time, right? But I was never driving 40 miles per hour for an extended part of my journey. So that's what average rate of change is. Average rate of change is just kind of averaging all of my slopes, essentially, of all of the points in my function. However, unless I was driving 40 miles an hour the entire time, I don't call it a slope, right? So a slope is constant. The average rate of change is taking non-constant, essentially non-constant slopes, right? It's changing the steepness of the curve, and it kind of evens them out. What would happen if this was constant? Only lines have slope. Any other function that you find this for, it's always just called an average rate of change. This is very important for calculus, to know the difference between a slope and an average rate of change. All right, let's take a look at our next page. Here we want to look at, okay, so we talked about lines have slope. Lines are the only thing that has a slope. So what else can we say about lines? Well, we know that lines are a polynomial of degree 1. They're always able to be written in the form y equals ax plus b. Or if we're calling this our slope, usually we'll call it m. So, or y equals mx plus b. Okay, so when we're talking about general polynomials, we usually label their coefficients in alphabetical order. Lines are special. We always say that the coefficient of x is our slope, and therefore we can recall it m. We just renamed it m. Okay, algebraically, we know that m cannot be 0, because then it would not be a line. It would be, or it wouldn't be a linear function. It would just be a constant function. It would be a horizontal line. Okay, and then graphically, we know that we can draw this with a slope of m. If m is positive, it will look something like this. If m is negative, it will look something like this. And where it crosses our y-axis, we call that point B, right? And we label that with the ordered pairs, 0, b. And then analytically, thinking about this from a logistical, a theoretical standpoint, we know that this is a function with a constant non-zero rate of change. So it is changing over time. It's not a flat line, it's not constant, but the rate of change is constant. And we call that my slope, which is m. F is increasing if M is positive and decreasing if M is negative. And we can call our initial value is just another way of saying the y-intercept. So initial value is another way of saying the y-intercept. That is a vocabulary term that your book and therefore Math Excel will use throughout the year. So initial value, just another name for the y-intercept. Let's take a look at our next slide here. We want to be able to take data, real world information, and see if we can correlate it to a line. So remember earlier, a couple weeks ago, we were looking at regressions, and we looked at linear regressions, meaning we took data and we found the line that fits the best between those points. And so some data we can do that for. Sometimes it looks like a line and sometimes it doesn't. So we want to be able to identify when does our information, our data look like a line and when doesn't it? And one really nice way to do that is to group your points together and say, does it look like I know where to draw the line and the line is pretty close to all of those points? That would be a strong correlation. So if the data looks like a line, it is strong. So our first example there is strong. Our first example underneath is also strong. So what's the difference between them? Well, one of them is increasing, right? The top one is increasing, so it would have a positive slope. So we say positive refers to the slope. Strong refers to the shape. So we have a strong, meaning it's shaped like a line, positive, meaning it's increasing, linear, meaning it looks like a line. We can also have strong quadratic correlations where our dots look like they form kind of a parabola shape. Something like that would have a strong quadratic correlation because it looks like a parabola. So we can't only have linear correlations, but in this class, we're focusing right now on linear correlations. In our second graph in the middle of the top, we're looking at now my points are kind of grouped together, but they're spread out a little bit more, but I can still kind of tell that they're increasing over time, right? So I can tell that it's increasing, but they're really spread out. And so I can put a line in the middle, but it's not going to be close to all of the points. And that gives us a weak. Now it's still increasing, so it's positive, and it's close to a line shaped, right? I couldn't say that that looks like a parabola. I couldn't say that that looks exponential. That the closest shape that I could call that is a line, but it's not very close to the line. It's a little bit spread out, so it is a weak positive linear correlation. We can do the same thing for negative. I could draw a line in this data on the bottom. It's not going to be particularly close to all of the points, but I can tell that the data is decreasing. And so that is a weak negative linear correlation. And then we have our last kind of data set here, and I can't tell if that's increasing or decreasing. It doesn't look like it really has a shape. It's just kind of everywhere. And so that has little to no correlation. Okay, I can't draw any shape in between that, right? If I draw a line this way, I can get close to some of the points, but I could also draw a line this way and get close to a lot of the points. And well, okay, so then what if I just started drawing lines everywhere, right? There's no particular line that I can draw that we can say that's definitely the line that gets the closest to the most points. And so that has no linear correlation. So linear correlation means it is close to the shape of a line. It's strong. It's almost close to the shape of a line, then it's weak. If it's increasing, it's positive. If it's decreasing, it's negative. Okay, looking at the next slide here, how do we know, how do we define correlation? Well, we have a coefficient of correlation, or a correlation coefficient. And so we can say that our correlation between the data and our line, if it's really, really strong, it's going to be close to positive or negative 1. So a 1 means that it's a line. If I have a correlation of 1, that means all of my points lie on a line. Okay, if it's negative 1, that means all of my points lie on a line with a negative slope. It does not mean that the slope is negative 1. It just means those points lie on that line with a negative slope. Okay, so if I have points something like this, not all of those points lie on the same line, but they're pretty close. So my correlation coefficient here could be about negative 0.89. I'm just making that up. It could be closer to 9.4. Those points are pretty close together. So it's going to be close to negative 1, but it's not going to equal negative 1 because the dots aren't all on the same line. Okay. If my correlation is, maybe my points are more spread out like this, they're still mostly linear. There's a few outliers there, but I can say almost all of the points are in this direction. Well, this is a little bit harder. This might have a correlation, still a negative slope, so it's going to be negative maybe 0.5. It's close, but it's more spread out, right? And then we can have, like our last example on the previous slide, we can have data points that are just everywhere. There's no way to tell where a line could go through that. And then my correlation would be really close to 0. So again, not to do with the slope. It has to do with how close those points are to forming a line. Okay. Let's take a look at quadratics. Now, I know that completing the square was covered in Algebra 2, but I wanted to review it, and some of you might not have seen the proof of why we can have a formula, we can have a shortcut for completing the square. So I'm going to prove the shortcut, and then from then on you can use it. So I did this with my Algebra 2 honors classes, so if you've seen this before, just kind of take notes, see if you can remember, maybe challenge yourself to try to work ahead of me. Okay, so we're going to start with a generic quadratic function, quadratic meaning degree 2, right? And our first step here is going to be to try to get the x's by themselves without a coefficient. So I'm going to go ahead and subtract c on both sides, and we get y minus c equals ax squared plus b. So my x's, whoops, bx. My x's are on their own side of the equation, but I also don't want a, so now I'm going to divide by a. So I have y minus c over a equals x squared. I have to divide everything by a, so that's b over a x. Okay, so now I'm set up. I can go ahead and complete the square. To complete the square, I'm going to work on the side and say my linear coefficient, the coefficient of x, is b over a. I want to multiply that by 1/2. So that's b over 2a. And then I want to raise that to the second power. So that's b over 2a squared. Okay, now why do I want that? This is the number that completes the square. This is the complete number. That's our magic number. And by adding that to both sides of the equation, I'm going to be able to factor a perfect square. So now I'm going to say y minus c over a plus my magic number b over 2a squared equals x squared plus b over a times x plus b over 2a squared. So now I want to factor this. In order to factor this, I want a number that multiplies to b over 2a squared and adds to b over a. So what two numbers multiply to b over 2a times b over 2a and add to b over 1a? And this is the trick. it's going to be our middle step, b over 2a and b over 2a. If I add them together, b over 2a plus b over 2a, think about it as 1/2 ba plus 1/2 ba, sorry, 1/2 b over a plus 1/2 b over a gives me 1/2 b over a. And if I multiply them together, then I get b over 2a squared. Okay, so that's the magic trick. That's why we needed that step to complete the square. So now I have y minus c over a plus b over 2a squared equals x plus b over 2a times itself squared. So that's the magic trick of completing the square. We had 2 steps that we had to pay attention to. The first one was finding our magic number in green, and the second one is using that magic number to factor it. And now I have a completed square. So now I want to solve for y again. And so here I'm going to subtract b over 2a squared from both sides. Y minus c over a equals x plus b over 2a squared minus b over 2a squared. Multiply everything by a and add c. So y equals a times x plus b over 2a squared minus a times b over 2a squared plus c. Okay, that is the completed square. Notice a couple of things. First, I have 1x, so that makes this my horizontal transformation. It has moved to the left by b over 2a, right? Secondly, I could write this as plus this whole thing, right? Instead of minus something, I can do it as plus a negative. I'm not distributing that negative because c was already positive. I don't need to mess with it. I'm just rewriting the minus. I'm grouping it together as a plus a negative. Okay, that is going to give us what's called vertex form. And vertex form is y equals a times x minus h squared plus k. So this h comes from this b over 2a. Remember how it shifted to the left, right? So the minus h lets us write it as a positive number. Lets us think about it as a rightward movement. Okay, h is positive. The minus makes it move to the left. Okay, so h equals negative b over 2a. Here's our shortcut. This is kind of our key, and I have it written on the next slide as well. And then k was this whole complicated thing, right? K was this whole complicated thing. So instead of memorizing that whole thing, what we can do is we can also say that k is our y value, right? K is our vertical shift. And so we can say that k equals the y value when our x is h, f of h. Isn't that how we find the y value for a given x value, like we saw in our first example? Okay, so we have this ordered pair. I'm going to put it in black up here. We have the ordered pair h comma k, and our shortcut, in order to write this in vertex form, our shortcut is that h equals negative b over 2a, comma f of negative b over 2a. And then we can substitute that in. I have my a value given. I can find h, I can find k, then I can find my vertex form. Okay, so that's my proof. Now you can use it. So let's summarize. Vertex form of a quadratic equation. For any quadratic function, f of x equals ax squared plus bx plus c, where a is not 0, meaning it has to be quadratic, not linear, can be written in vertex form. F of x equals a times the quantity of x minus h squared plus k. The graph of f is a parabola with vertex h comma k. That's why it's called vertex form. Vertex is the point of change, right? This point here is the vertex, h, k. An axis of symmetry, x equals h, right? It's going to go directly through that vertex, where h equals negative b over 2a and k equals f of h. If a is positive, the parabola opens upward. If a is negative, the parabola opens downward. Okay, we used this a lot in Algebra 2 in our quadratic function, but we'll also see examples throughout pre-calculus, such as this one. So in this example, we want to use algebra and describe the graph of the equation. So if I want to describe this, I need to be able to tell you what the transformations are, right? And in order to do that, I need to put this into vertex form. In vertex form, I can see the transformations, right? Let me go back. I can see this is my sideways shifting, K is my vertical shifting, and A is my stretch, vertically or shrink. Okay, so in vertex form, we can see all those transformations. So let's see if we can write this in vertex form. And let's go ahead and try using the shortcut. Our shortcut, remember, is that I need to find the vertex, hk, in order to write it into vertex form. H equals negative b over 2a. So I need to know my a is negative 4, b is 12, and c is negative 8. So negative b is negative 12 divided by 2 times a is negative 4. That gives me, that gives me negative 12 divided by negative 8. 4 goes into both of those, and negative divided by a negative is positive. So that is, 3, there we go, 3 halves. There's my h value, 3 halves. Now I need k. To find k, I substitute f of h. So that's f of 3 halves. Let's go ahead and substitute it into the equation. And then remember, you have a calculator, so you don't have to do all the calculations by hand. Negative 4 times 3 halves squared plus 12 times 3 halves minus 8. I'm going to go ahead and do this by hand. Negative 4, if I square a fraction, I square the numerator and the denominator. That's 9/4 plus 12 over 1. So I'm going to reduce that. 6 times 3 is 18 minus 8. The 4 over 1 reduces, so that's negative 9 plus 18 minus 8 is 10, gives me 1. Okay, so let's see if we can put this into vertex form. Vertex form, y equals a times x minus h squared plus k. Do I know a? We didn't have to do any calculations for a. It was already given. Negative 4 times x minus h is 3 halves squared plus k is 1. There's my vertex form, but that wasn't my goal. My goal is to describe this. So to describe this, I would say vertical stretch by 4, reflect over, if I'm reflecting vertically, that's over the x axis, right shift by 3 halves, upward shift by 1. That's my description. Go ahead and put the function into your calculator and see if it matches. You should have a graph that looks like this. Something like that, pretty close. I think it's actually going to cross. It's a pretty steep graph, like this. All right. So let's take a look at finding the vertex and axis of symmetry for this next quadratic function. Use the vertex form of the quadratic function to find the vertex and axis of symmetry. So when it says axis, it means the axis of symmetry, always, for quadratics. So the vertex and the axis of symmetry of the graph f of x equals 2x squared minus 8x plus 11. Rewrite the equation in vertex form. Okay, so let's start by finding our vertex. Again, we're going to label A is 2, B is -8, C is 11. To find H, I need -b over 2a. You should recognize that as part of the quadratic function, right? We mentioned that in class. -b over 2a, which is negative of -8 becomes a positive 8 divided by 2 times 2. 8 over 4 is 2. There's H. Next, we need K. K is f of H. So I'm plugging H into F, so that's f of 2. Gives me 2 times 2 squared minus 8 times 2 plus 11. 2 times 4 minus 16 plus 11. 8 minus 5 equals 3. So we've got our point here is 2, 3 is the vertex. Okay, found the vertex. We also need the axis, or the axis of symmetry. Well, I know that this is going to be an upward opening parabola with a vertex at 2, 3. So the axis of symmetry goes right down the middle, meaning it goes straight down in a line. X equals 2 is the axis. It will always be your H value for an up and downward facing parabola. And then also rewrite the equation in vertex form. So this one needs a little bit of work. Y equals a times x minus h squared plus k. I'm going to write the answer above it. Y equals a, 2, x minus h, 2, squared plus k, 3. So we got the axis of symmetry. Well, the graph, I kind of sketched it down at the bottom and in vertex form. So let's draw this graph a little bit better. So I know that it moves to the right by 2 and up by 3. A little trick, if you look at the standard form, the non-vertex form, that also gives you the y-intercept. So I know it's going to be, I also know it's going to be steep. So there's a sketch of my graph, knowing that it crosses at 11 with our little trick with the y-intercept that I just showed you. Knowing that this is 2, 3 as well. All right, we're almost done. On our next slide here, we're looking at the characteristics of a quadratic function. So we looked at the characteristics of a linear function as well, right? The quadratic function characteristics are going to be different, but some of them are kind of similar. So verbally, we can say it's a polynomial of degree 2. That's what makes it quadratic. Algebraically, we have 2 forms of writing it. We have standard form, and we have vertex form, where our vertex is hk. And h is negative b over 2a, and k is f of h. We know graphically that this is a parabola. The vertex is hk, we mentioned that. The axis, or axis of symmetry, is x equals h. We saw that in the last example. We know if a is greater than 0, it opens upward. And if a is less than 0, it opens downward. Our initial value, remember that was one of our vocabulary words earlier. Our initial value, also called the y-intercept, is f of 0, which will be c. I mentioned that on the last slide. And the x-intercepts can be found with the quadratic formula, which we reviewed last class. And this is what I was mentioning again, is that within the quadratic formula, we see that part of h, negative b over 2a. The proof that I did earlier is almost the proof of the quadratic formula. It's almost the proof of the quadratic formula. Okay, one last thing. This is it. This is the last one. The height s and the vertical velocity v of an object in free fall are modeled by this equation that's quadratic, okay? As well as we have another equation here that's linear. So this one is quadratic, this one is linear, right? Now, these two equations have a very close relationship that we will be able to talk about in more detail at the end of the year, being that s of t, the position, and v of t, the velocity, are derivatives. So v of t is the derivative of s of t. You might have heard that word derivative before. I know some of you have been looking it up. After our last chapter, it came up in a couple office hours. I don't expect you to know derivatives yet, not at all. But this is one of the examples that we'll be able to talk about in more detail at the end of the year. T is time, always given in seconds. G is gravity. Gravity is a constant. So even though it's listed here as a variable, that's because it depends on the units. If your units are in feet, G will always be 32. If your units are meters, G will always be 9.8. So G is a constant. Looks like a variable, but just like pi, it's a constant. It just G depends on, its value depends on the units. V with a little subscript 0, it's read V naught, is the initial vertical velocity, the initial vertical speed, so to speak, okay? S naught, the initial position, the initial height. That little subscript of 0 means where it was when no time has passed. So that subscript naught means at the very beginning. In general, if we have A naught or A sub 0, that's always what it means. It means at the very beginning before any time has passed. If you need these equations on a homework assignment or on an assessment, I will always tell you to refer to them for now. Okay, that's the end of the video. I know it was a little bit long. You don't have any practice problems to finish before next class, because next class is going to be a practice class. So if you have any questions, feel free to reach out to me, but just know we will also be practicing as a class during our next class meeting.